It is the 10th of September, 2025, approximately 11:49 a.m. Continuing on where we left off, the cycle notation from earlier, going into, gosh, where were we? Actually, I believe we were at tau sigma. So let's take a look at that, shall we? Yes, marker's done. For tau sigma, apply sigma, then tau, which would be step 5. Let's rewrite tau and sigma here so that way we have a better idea of what we're working with. Yeah, okay. I can sort of see the limits of where I can write on this board. So tau, we had that equal to 14, 2, 9, 15, 13, oops. $11, 5, whoops, why did I put that down? Okay, so 114, 2, 9, 15, 13, 4, and let's see here, open parentheses 114, close parentheses, open parentheses 2, 9, 15, 13, 4, open parentheses 3, 10, close parentheses, open parentheses 5, 12, 7, close parentheses, open parentheses 8, 11, close parentheses. Sigma is equal to open parentheses 1, 13, 5, 10, so open parentheses 1, 13, 5, 10, close parentheses. Then we have open parentheses 3, 15, 8, close parentheses, open parentheses 4, 14, 11, 7, 12, 9. That's what we have for sigma and tau. trying to pick up the pieces of where we left off. So, yeah, okay. So we track 1 here. Go 1. By sigma, that gets us to 13 by tau. 4. Sigma, 14, tau, and this would give us, open parentheses 1, 4, close parentheses, right? And then we go track 2, sigma to 2, tau to 9, sigma to 4, and tau to 2, which would give us 2, 9. Track 3. To 15 via sigma, 15 to 13 via tau, 13 to 5 via sigma, 5 to 12 via tau, then 12 to, well, actually I can just do that here. 12 to 9 via sigma, and then from 9 to 15, that is via tau. And if we continue along this path, right, so we'll go and we get 3, 13, open parentheses 3, 13, 12, 15, 11, 5, close parentheses. And tracking that, well, so that's what we get for there, and we can sort of add that to our menagerie of what belongs to tau sigma, right? So all of these go into the menagerie, and we can proceed from there. Oops. Oh well. Just needed those to kind of see where I was back then. Now, let's move on to track 8. Tracking 8, what does that get us? Well, it gets us 8, open parentheses, 8, 10, 14, close parentheses. Therefore, tau sigma, remember, our menagerie, so open parentheses 1, 4, close parentheses, open parentheses 2, 9, close parentheses, open parentheses 3, 13, 12, 15, 11, 5, close parentheses, open parentheses 8, whoops, can't see that far. Right, open parentheses 8, 10, 14. Okay, now on to tau squared sigma. And let's get, the closer we get to finishing off this one, right? So let's see here. Tau squared sigma. Step 6. Tau squared from step 2. So compose that with sigma. What did we get? I can't remember. Gosh dang it. No, sorry, that's just yeah, from tau. Okay. Using, okay, so the actual tau thing from step 2, what tau is actually equal to from step 2. Each cycle squared then compose with sigma. Tracing 1 produces the 13 cycle. Open parentheses 1, 2, 15, 8, 3, 4, 14, 11, 12, 7, 5, 10, and with 6 and 9 fixed by tau squared sigma. So what we get then is tau squared sigma is equal to this. So it's like, yes. Yeah. It's not really a notational thing. So all we had to really do is trace 1 in that case. Which works. Now collecting all the decompositions. What does that get us? Well, cycle is equal to, open parentheses 1, 13, 5, 10, open parentheses 3, 5, 8, close parentheses, open parentheses 4, 14, 11, 7, 12, 9, sigma, right? So, and then let's show tau. Tau is equal to, open parentheses 1, 14, open close parentheses, open parentheses 2, 9, 15, 3, 13, sorry. 13, 4, close parentheses, open parentheses 3, 10, close parentheses, open parentheses 5, 12, 7. I'm just going to hurriedly jot these down because you can just go back and see what they actually are, right? So, but I like to have them all in one place. Equals, so, oops, yeah, just writing these down as well. So, can I actually write them all down on this board? Let's see. Only so much space. So, oh boy. Tau squared, let's see, 1, 2, 15, 8, 3, 4, 14, 11, 12, 13, 7, 5, 10. There we go. All right, so that's it for exercise 2. Let's move on to exercise 3. So exercise 3, we have for each permutation, whose cycle decomposition was computed in exercises 1, 2, its order. For each permutation whose cycle decomposition was computed in exercises 1 and 2, we want to determine its order, right? So let's go through that one step at a time. Start with set. We'll have a set A just for exercise 1 and a set 2 just for exercise 2. We'll go through each one, checking the order. So, well, actually I should say, intuitively, if a permutation is a product of disjoint cycles, its order is the least common multiple of the cycle lengths. A single k cycle, of course, would have order k. So, with set A, we had sigma is equal to open parentheses 1, 3, 5, whoopsies, close parentheses, open parentheses 2, 4. So what would the order of this be? Well, it's equal to the least common multiple of the cycle lengths. Cycle lengths we have are 3 and 2, so the order of sigma then would be equal to LCM 3, 2, which would equal 6, right? Nothing too dramatic. Now let's go on to tau. Tau is equal to open parentheses 1, 5, close parentheses, open parentheses 2, 3, close parentheses. So what's the LCM of this? Both of them are equal to 2. Well, both of them have order 2, so the order of tau equals 2. Simple enough. On to the next one. What did we get for sigma squared? Equals open parentheses 1, 5, 3, close parentheses. Well then, the order of sigma squared is equal to 3. Why is that? Well, right, what's the least common multiple of 3 in itself? I mean, there's no other cycle, right? So, unless you're saying like 1, then, well, it's still 3, right? So, so there we go. If you had an infinite one, you know, we could say the least common multiple of that, and infinity is infinity. No. Yes, actually. So sigma tau is equal to open parentheses 2, 5, 3, 4. And the order of sigma tau is equal to LCM 4, which is equal to 4. Simple enough. It's the least common multiple of the only thing available, which is 4. So how about this? How about tau sigma is equal to open parentheses 1, 2, 4, 3, close parentheses. Well, that's simply equal to 4 because it's the only thing again, right? So you can see that. So, yeah. Now let's go on to the next one. Well, actually, yeah, my brain is going foggy for that, but let's go on to this last one here, which is tau squared sigma, which is equal to sigma. So that, of course, is just equal to the order of sigma, which is equal to 6, as we determined earlier. So nothing more to really show for set A. Now let's move on to set B, where things get a little more interesting. So for set B, for sigma, right, we had, let's go ahead and put set B up here. This is for exercise 2. So for sigma, we had open parentheses 1, 13, 5, 10, close parentheses 3, 15, 8, close parentheses, 4, 14, 11, 7, 12, 9, close parentheses. And what do we have there? Well, we've got 4, 3, 1, 2, 3, 4, 5, 6, 6. Right, so the order of this would just be equal to the least common multiple of 4, 3, and 6, which is 12. So the order of sigma is 12. Now let's move on to sigma squared. No, actually tau. Let's move on to tau. Tau is equal to open parentheses 1, 14, close parentheses, open parentheses 2, 9, 15, 13, 4, open close parentheses, open parentheses 3, 10, open parentheses 5, 12, 7, close parentheses, open parentheses 8, 11. Let's see here. So the order of tau then is equal to the LCM of these, which are, is the order of these three, the disjoint cycles, right? So 3, and then we have 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 1, 2, 2, 5, 2, 3, 2. All right. What's the least common multiple of all of these? It's weird because I wouldn't expect it at first, but 30. You know, that's a surprisingly big number for all of these small numbers, right? But 'tis what it is, right? So let's go on to sigma squared. So sigma squared is equal to open parentheses 1, 5, close parentheses 3, 8, 15, close parentheses, open parentheses 4, 11, 12, close parentheses, open parentheses 7, 9, 14, close parentheses, open parentheses 10, 13, close parentheses. So what's the order of sigma squared. Well, same process as usual. 2, 3, 3, 3, 2. What's the least common multiple of that? Well, don't know about you, but that looks like 6, which in fact it is. Okay. Let's go on to sigma tau. So sigma tau is equal to, open parentheses, 1, 11, 3, close parentheses, open parentheses, 2, 4, close parentheses, open parentheses, 5, 9, 8, 7. You know, I naturally want to put a comma there. It just seems aptly placed. But I won't. Well, no, I will probably do that again. But 10, 15, close parentheses, open parentheses, 13, 14, close parentheses. So, what does this get us for the the order of sigma tau? Well, the order of sigma tau, as is per usual, is equal to the LCM of each of the orders of the LCM of all of the orders of each of these disjoint cycles, right? So 3, 2, what is this? 1, 2, 3, 1, 2, 3, 6, 2, right? So 3, 2, 6, 2, which is equal to 6. Now let's move on to the next one. Sigma tau. Whoops, sorry, I was about to repeat myself. Tau sigma. That's equal to, open parentheses, 1, 4, close parentheses, open parentheses, 2, 9, close parentheses, open parentheses, 3, 13, 12, 15, 11, 5. Yes, wait, no, hold on a minute. 12, 15, 5, yes, okay. Open parentheses, 8, 10, 14, close parentheses. So what's the order of tau sigma? We've got 2, 2, what is that? 3, 3, so that's 6 again, and then this is 3. So the same thing as before. It's just that the 6 is in a different place, which something could be said about that. But I'm just going to sort of leave that as it is for now. So the order of tau is equal to the LCM of all that, which is equal to 6. Now, let's move on to the final one in set B. So, tau squared sigma is equal to, open parentheses, 1, 2, 15, 8, 3, 4, 14, 11, 12, 13, 7, 5, 10. All right, what's the order of this? Well, that's one disjoint cycle, right? So whatever it is, it's going to be, what is it? So it's going to be the LCM of that single thing, which of course would just be that. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, that's 13. So the order of tau squared sigma is equal to 13. Single 13 cycle, that begets order 13. So all requested orders are computed. Now let's move on to exercise 4. Oopsies. So exercise 4 gets a little bit more interesting. We're asked to compute the order of each of the elements in the following groups. Which are S sub 3, S sub 4, those symmetric groups. So the intuition for this is an element's order is the least common multiple of the lengths of the cycles in its disjoint cycle decomposition, right? So classify elements by cycle type and then record the order of each of them. So that way we don't have to go through and pick all these out by hand. I mean, but you still can, and that's still a thing to do, but let's go ahead and show this a bit more rigorously. So S sub 3, abstract classification. Type 1, AB, ABC. So these are the types here. So we have the identity. We have open parentheses AB, close parentheses, open parentheses ABC, close parentheses, and representatives. Okay. And this would be 1, and then open parentheses 1, 2, close parentheses, comma, open parentheses 1, 13, sorry, open parentheses 12. No, sorry. Let's see here. No, that is 1 and 2, because we're working with S3. Silly me. Now, this is open parentheses 1, 2. You see, a simple comma would be so valuable, but then it looks like an ordered pair. Can't use that. It looks like coordinates, I mean to say, because then you could go, R3, open parentheses 1, 2, open comma, open parentheses 1, 3, close parentheses, open parentheses 2, 3, close parentheses. And for this case, we'd have 3 of them all up in a row, right? So this would be 1, open parentheses 1, 2, 3, close parentheses, and then we'd have open parentheses 1, 3, 2, close parentheses. So let's get to, don't care, let's see, that count. So this is basically just, okay, how many of them are there? Well, there are 1, single identity, 3 of these, 2 of these. What's the order of each of these, right? Really, this should be ideally on that side if we're going by, sort of a left to right progression in a way, in terms of like reading a thing, right? But this would be, the order of this is 1, the order of this is 2, the order of this is 3, using the same thought process that we did earlier, taking the least common multiple of each of them, each of the orders of each of these disjoint cycles. We could get explicit with this, right? So it's like, what is it? 1, 3, and 2, 3. And this would be 1, 2, 3, 1, 3, 2, so on and so forth. Don't necessarily have to, but you could. So let's look at S sub 4. Now for part B, we're looking at the symmetric here with 4, so S sub 4. We just do the same sort of thing. We have these different types. 1, open parentheses AB, close parentheses, open parentheses AB, close parentheses, open parentheses CD, close parentheses, open parentheses ABC, close parentheses, open parentheses ABCD, close parentheses. And then what would be the representatives of this, right? So you get the same sort of thing. Which is to say, 1, and then for each of these, sorry, what I meant to say is like, before, whenever I said like explicit permutation order table, what I meant is like, you have like the permutation, right? And then you have 1, 2, 3, and then you have the order of that, 1, 2, and then you list another permutation. Well, you match up each order to each of them. That's what I meant. Not that, we're not listing the actual elements. I mean the actual cycles. So, in this case, we have open parentheses 1, 2, close parentheses, open parentheses. Well, let's just continue on, shall we? I can mention all of these, which I kind of will. Oh, we're almost out of space. Open parentheses 1, 2, close parentheses, comma, open parentheses 1, 3, close parentheses, comma, open parentheses 1, 4, close parentheses, comma, open parentheses 2, 3, close parentheses, comma, open parentheses 2, 4, close parentheses, comma, open parentheses 3, 4, close parentheses, and so on and so forth, right? So, how about let's keep a count going for these, just as we did before. And let's see if you can actually see the order if I were to put it over there on the left. Yes, you can. Okay, very good. So the order to be an underscore. Now, let's look at open parentheses. AB, close parentheses, open parentheses, CD, close parentheses. So this one would just be, right, 1, 2, oh goodness, 3, 4, okay. Open parentheses, 1, 2, close parentheses, open parentheses, 3, 4, close parentheses, comma, open parentheses, 1, 3, close parentheses, 2, 4, open parentheses, 2, 4. It's getting hard to say all of the parenthesis notes. Okay, so let's just try and stick to it. Open parentheses, 1, 3, close parentheses, open parentheses, 2, 4, close parentheses, comma, open parentheses, 1, 4, close parentheses, open parentheses, 2, 3, close parentheses. Right? This goes on and on and on. So what would the count be here? 1, 6, 3, 8, 6. We haven't gotten to that yet, but that's fine. I'm just putting these down here for later. We'll discuss them a bit more fully in a bit. Not really, because we don't really need to, because the rule still applies with the LCM and each of these disjoint cycles. So, how about this case? Well, all 3 cycles, this would just be all 3 cycles in S4, and this would just be S sub 4 technically. All 4 cycles in S sub 4. You could just call them S4, and that's what I think a lot of people do, but it's just like, that's S4. It's different. No, but, yeah. Okay, and that's it for exercise 4. Now let's move on to exercise 5. Yeah, and you can see, the order, why that is the way it is, via LCMs of each of the disjoint cycles, right? So let's continue on. So for exercise 5, find the order of open parentheses 1, 12, 8, 10, 4, close parentheses, open parentheses 2, 13, close parentheses, open parentheses 5, 11, 7, close parentheses, open parentheses 6, 9, close parentheses. So find the order of this, right? And we do it in the exact same way. I don't know why this is just one. Why is this one question? Why is this an exercise? It's weird. Because it's usually like find the order of all of these, right? But this is not so. So intuitively for disjoint cycles, right, the order of the product is the least common multiple of the individual cycle lengths. In this case, order sigma is equal to the LCM. How many do we have? We've got 5, we've got 2, we've got 3, we've got 2. So 5, 2, 3, 2, What does that get you? Well, I guess probably because there's two of these, two twos, maybe that's it, 5, 3, 2, but that doesn't really change anything, that just gets you 30 regardless, right? So the order of sigma is equal to 30. Unless, of course, I wrote it down wrong, I don't know. That's interesting. I wouldn't have considered that to be an exercise, but I mean, it's nice if it's the case and I didn't just like copy the exercise from something else, right? But I'm pretty sure that's directly from dominant input. I don't have the textbook with me, so I can't confirm. But if it's a case like we had with exercise 3 earlier, what was it? Exercise 3 in 1.2? Yeah, where I just completely skipped an exercise that I didn't include in my notes. That could be what's going on here, where I just like, this was actually part of some other problem, and I put it over here as its own exercise. That would be hilarious. Hopefully that's not the case. Hopefully this is actually exercise 5. But, yeah. Okay. Let's move on to exercise 6 then. But all of these should be what's in the textbook, because that's what it was whenever I wrote it, so. I'm willing to accept a gift, if indeed it was. So let's go on to exercise 6, which is write out the cycle decomposition each element of order 4 in S sub 4. Write out the cycle decomposition of each element of order 4 in S sub 4. Oh, okay. So in S sub 4, that's, I said it twice, and I say it twice partly because, like, it sort of sticks to the memory a bit better if you say something twice, right? But it's also because, look at this handwriting. There's no way, right? There's no way. But there it is. Okay, so in S sub 4, an element has order 4 if and only if its disjoint cycle type is a single 4 cycle. Transpositions and products of 2 disjoint transpositions have order 2, 3 cycles have order 3, so on and so forth, right? So, well, I mean, we're talking about S4, so there's not much so forth, right? It's just the thing we were talking about. So let's look at that a bit more rigorously and point out exactly, explicitly what those ones are. So I guess a proof in a way, right? So the elements of order 4 in S sub 4 are precisely the 4 cycles. Enumerating all four cycles on the set 1, 2, 3, 4. What does that get us? Well, that gets us open parentheses 1, 2, 3, 4. Yeah, I guess my problem with cycle notation is like, why not just make them sets in a way? But it's fine. I mean, like I don't know. Oh, well, I kind of know. I kind of see it. Because they're different things, right? So, but open parentheses 1, 2, 4, 3, close parentheses, and then we have 1, 3, 4, 2, close parentheses, and then we have open parentheses 1, 4. So you're just changing these around, you see. 4, 2, 3, close parentheses, and then we have, then we have 1, 4, 3, 2, close parentheses, so on and so forth. I keep saying that, but everybody has their own little internal vernacular. So each listed permutation is already in cycle decomposition. A single 4 cycle. And a 4 cycle has order 4. No other cycle type in S sub 4 yields order 4. That completes exercise 6. Now let's go on to exercise 7. Oh, I gotta be careful not to get dry erase marker in my coffee there. Probably wouldn't taste too bad. Well, I don't know. If I try dry erase marker. I'd probably put something in it that tastes bad to prevent people from choking on it, right? I don't know. Maybe not. Wouldn't be good for my stomach anyhow. Some people are able to eat like aluminum cans and just be completely fine. I don't understand that. I mean, like if you have a gizzard, that makes sense because it's just rocks in there. But I mean, you'd think like it would puncture the gut. But that's not the point. No, but it is a point. No. But so exercise 7. We have to write, don't have to, we'd want to, write out the cycle decomposition come on now, form of each element. Let's just go back to writing normal L's and 1's. Because I feel like the underscores and all the other notation I have should be able to withstand that. In S4, so write out the cycle decomposition of each element of order 2 in S sub 4. Intuitively, in S sub 4, an element has order 2 precisely when its cycle decomposition is a product of disjoint 2 cycles, right? So this includes both single transpositions and products of 2 disjoint transpositions. So let's look into how we look at that a bit more rigorously, right? So, as is our per usual, our, what is it? Prerogative. Yeah, this is our duty, prerogative. Yeah. Okay, so proof. The transpositions two cycles in S sub 4 are open parentheses 1, 2, close parentheses, open parentheses 1, 3, close parentheses, open parentheses 1, 4, close parentheses, open parentheses 2, 3, close parentheses, open parentheses 2, 4, close parentheses, open parentheses 3, 4, and each of these has order 2. I might go into like describing exactly what a permutation is, so that way we have something a bit stronger to work with, because it's kind of like, well, you know, you just sort of rearrange all of these things that could be in S4, these sort of individual elements like 1, 2, 3, 4, right? So you do that, put that inside of a disjoint cycle and call it a day. But I feel like, you know, there is a more rigorous way of saying that, but that's just what it is, right? But let's continue along this journey. So the transpositions, 2 cycles in S4 are these. Now, how about the products of 2 disjoint transpositions in S sub 4? Those each have orders which are 2 for their disjoint cycles, and we can progress that way, looking at them as such. So the products of 2 disjoint transpositions in S sub 4 are open parentheses 1, 2, close parentheses, whoopsies, that's supposed to be an underscore, open parentheses 3, 4, close parentheses, comma, well, the next one is open parentheses 1, 3, close parentheses, open parentheses 2, 4, close parentheses, open parentheses, yeah, 1, 3, 2, 4, 1, 3, open parentheses 1, 3, close parentheses, open parentheses 2, 4, close parentheses, comma, open parentheses 1, 4, close parentheses, open parentheses 2, 3, close parentheses, and each of these has order 2, right? So each has order 2. We've looked at that. And we have listed all of them. We have listed all of the elements of order 2 in S sub 4, so we're good to go. Exercise 8. So for exercise 8, prove that if omega is equal to 1, 2, 3, continuing on, then I meant to put comma, but my mind said E because you were about to write then. Then S sub omega is an infinite group and we can't really say this. I mean, this doesn't really prove it, but you know, this whole infinity is equal to infinity. So can't do that. Can't. No doing that. Well, that's an empty set. So problem with working with so many symbols is that they all mean something. No, but so what if you try to write something that means something else? It means something, you know. But do not say infinity factorial is equal to infinity, right? So I mean, do I really even need to say that? I mean, yeah, I guess so. But it doesn't really have much to do with. Suffice to say, let's just leave it at that. But intuitively, you'd exhibit infinitely many distinct permutations in S sub omega. A simple choice is one transposition for each n, swapping the pair 2n minus 1 and 2n, and fixing everything else. These are all different, so let's see that a bit more rigorously. So for the proof, for each n within the positive integers, define sigma sub n to be within S sub omega. Find that by find sigma sub n to be within S sub omega by omega sub n times, oh well, no. Okay, so omega sub n of 2n minus 1. Is that rather, think about this, because I'm trying to see that a bit more. Oh, my back, okay. Okay, so sigma sub n, then open parentheses 2n minus 1, that is equal to 2n, sigma sub n 2n, that is equal to 2n minus 1, and sigma of k is equal to k for all k within omega, with the exclusion of 2n minus 1 and 2n. So yeah, sigma sub n of 2n minus 1 is equal to 2n. Sigma sub n of 2n is equal to 2n minus 1. Sigma sub n of k is equal to k for all k within omega, with the exclusion of 2n minus 1 and 2n. Now, so what do we have from that, right? What's the narrative through line? Well, therefore, sigma sub n is equal to 2n minus 1, 2n, well, open parentheses, 2n minus 1, 2n. And that is so therefore, it is this, but it's also a transposition. So, a bijection of omega. So sigma sub n is within S sub omega. And we claim that the sigma sub n are pairwise distinct. If I does not equal j, then sigma I of 2I minus 1 is equal to 2I, which is not equal to 2I minus 1, which, as we saw earlier, well, should be equal to sigma of 2I minus 1. So okay, since sigma sub j fixes 2I minus 1 when j is not equal to I, right? Okay. Since I, it's supposed to be sigma sub j, sorry. It's not equal to sigma sub j. Since sigma sub j fixes 2I minus 1, not 2, minus 1, when j is not equal to 1. Therefore, sigma sub I is not equal to sigma sub j. Hence, the set containing sigma sub n, such that n is contained within the positive integers, is an infinite subset of S sub omega, which means S sub omega is infinite. Right? Okay. There's no repetitions. It's just these are pairwise distinct. Each of these transpositions make up an infinite subset. And if you have an infinite subset, if you have a set and within that set you have an infinite subset, the set itself is infinite. And in this case, the symmetric group S sub omega is an infinite group, right? So go ahead and pause it here for now, and we'll pick up with some more of it here in a moment.